So Dalton's atomic theory remained largely unaltered for almost 100 years. And then, right at the beginning of the 20th century, the 1900s, people started to do some experiments that challenged ideas of this first atomic theory. And there are three really key experiments here. The first one, I'm going to talk about all of these, is J.J. Thomson. And he discovered the electron. The second sort of really important experiment is a guy called Mulliken, and he determined the mass and charge of electrons. So he completed the characterization of the electron. And then finally we have Ernest Rutherford, and what he did was determine the nuclear model of the atom. So we're going to talk through each of these three experiments and talk a little bit about some of their consequences. So as I mentioned, this was all happening right around the beginning of the 20th century. So in 1897, J.J. Thomson discovered through the use of cathode ray tubes that cathode rays, and I'll explain what they are in a moment, that are emitted from a charged plate were made up of negatively charged particles. And he couldn't figure out exactly what the mass and the charge of these particles were, but he could figure out the ratio of the mass to the charge, and it was found to be a lot less than anything that had ever been observed for any known atom. So how he did this was by, a lot is relying on the fact that charges that are of the same charge repel, or of the same sign, repel one another, and charges that are of opposite electrical charge will attract one another. So what he's got here is a big long tube that has a bunch of stuff inside it, but he can pump out all of the air. So it's got a bunch of metal plates and other things in there, but he can pump out all of the air from here, so there's no gas in here. And on the inside of his tube, at the far end of it, he's coated it with a material called phosphorus that glows, and it glows green if any charged particle hits it. So before this guy is hooked up, you see no glow on the end on your little screen there. Now, at the far other end, he has a metal plate, and that metal plate is called a cathode, and it's connected to the negative end of a battery. So what that means is it's going to repel anything that is negatively charged down the tube. Okay. Now, the other terminal of the battery is connected to a metal plate, or in this case they've illustrated it as a metal cylinder that has a hole in it, and that is positive. So that's going to attract negative things. Now the reason why it's got a hole in it is because negative particles were leaving the cathode as a kind of a broad pattern, but once they pass through that metal plate with a slit in there, you got a beam. All right. Now that beam of negatively charged particles travels down the tube, and you guessed it, it hits the screen and it makes a glowy green dot. Okay, so when you hook this thing up to the battery, you get a glowy green dot. And when you take the battery away, the green dot goes away. So what that's telling you is a negatively charged particle leaves this plate, travels down the tube, and hits the far end. Okay, so what? So then the question becomes, what is this particle? What is this thing that they're calling a cathode ray? So Thomson does a couple of things that are very clever. He puts another set of plates in that he hooks up to a different battery, but one where he can control the voltage. And these particles, because they are negative, will be attracted towards the positive plate. And he can flip the charges on the plate, and he can make it go down, and he can vary the voltage, and he can make it hit at different levels, right? So he makes a very careful chart of the voltage on these plates against where they are hitting on his screen. And he's got a little measuring device that is taped to the outside of his screen to help him with that. The other thing he knows is that charged particles are affected by magnetic fields. So he gets himself a couple of big magnets, and he moves them closer and further away to the sides of his beam. And again, he can make it go up and down, and he makes some careful observations. And you can actually do this yourself in physics lab. And out of all of these observations, he's able to get the mass to charge ratio of this particle. And it looks like that whatever's coming out of here, he knows it's negative, and it looks like it's really smaller than a hydrogen atom. It looks like it's part of an atom. So he proposes that these rays are subatomic particles, which we now call electrons, and we give the symbol E superscript minus. Now, this is in violation of Dalton's first postulate that said that atoms are indivisible, right? We seem to have observed what is a subatomic particle. And so as a result, people were very excited to try and develop a new atomic theory that was an improvement on Dalton's. So it was Richard Millikan that determined the charge on the electron, and he determined the charge to be negative 1.6 by 10 to the minus 19 coulombs. So Millikan has the charge, Thomson has the mass on the charge. He knows what this number is. Richard Millikan knows what this number is. If you put that together, you can get the mass, right? Yeah? The charge times the mass on the charge ratio is just going to give you the mass. Multiply those two together. There we go. And it was determined that the mass of the electron was 9.1 by 10 to the minus 28 grams. And that is way smaller than a hydrogen atom. This is very, very clearly part of an atom. It's a subatomic particle. So people at this point normally ask, well, how the heck did he do it? Well, what he did was this. He created some oil drops, he put an electrical charge on them, and then he levitated them using an electrically charged plate. So I'll show you a picture of his setup. He has a little atomizer that sprays oil, and the size of the nozzle makes certain that the size of the oil drops is always the same, right? So you probably notice that an eyedropper always produces the same size drop. So he's got a whole bunch of these oil drops, and he lets them fall through a plate that has a hole in it, right? So again, he's generating a beam of these oil drops, if you will. Now, the plate that they're falling through is electrically charged, and the plate that they're falling towards is also electrically charged. And so what's going to happen is these oil drops are going to fall down. They don't have any electrical charge on them, and they won't be influenced by the fact that these plates have an electrical charge. But then what Millikan does, which is really, really clever, is he uses X-rays to knock out charged particles, to ionize the charged particles that are making up, or to ionize these oil drops, to knock out electrons from these oil drops, right? And so what he ends up with is a bunch of oil drops falling down that are electrically charged. And what he finds is that he can adjust the voltage on these plates until he gets to the point where the electrical repulsion from the plate is equal to the gravity acting on the plate, and he can figure out the charge. And when he does this, he finds that the charge on the oil drop is always a whole number multiple of minus 1.6 by 10 to the minus 19 coulombs. And what that means is that's the smallest possible unit of negative electrical charge. That's the charge on the electron. So these guys are always losing a whole number of electrons, and so the charge that they generate is always a multiple, a whole number multiple of that number. That's the charge on the electron. So at this point, we know that there is a small, very, very light, negatively charged particle called the electron. So whatever makes up the rest of the atom has to be positively charged to offset the charge on the electron. So Thomson proposes like the simplest model possible. It's called the plum pudding model. And some of you guys talked about this in your discussion in class. And so Thomson says that the positive part of the atom is just like a big ball of dough, and it's really dense and quite heavy. And then embedded in that are these tiny little electrons like pieces of fruit, like plums in a pudding. And those plums are negatively charged. So yeah, that's the general idea. It's kind of like the simplest model you can think of. There's this like doughy stuff that's positively charged, and then you put into that these small electrons. Okay, so as long as the charge on the dough is equal and opposite to the number of electrons you have, you're going to get a neutral atom. All right. So, seems reasonable. Everybody now wants to test Thomson's plum pudding model of the atom. So, on the same timeline as all of this is happening, people were discovering radioactivity. And this was done by a bunch of people in Europe, namely Henry Becquerel and Pierre and Marie Curie, who were a married couple. Over in New Zealand and then later Canada and England was Ernest Rutherford. And what they discovered is that some atoms just spontaneously are unstable, and they just like emit subatomic particles. They emit particles that are smaller than a whole atom. Now, these two particles were found to be of two types. The first type investigated were alpha particles, and it was a bit of a mystery as to what alpha particles were. They called them alpha just because they were like type 1. The second type of particle that people detected being emitted were what were called beta particles, just, like AB, like beta is just like type 2. And it was fairly quickly recognized that beta particles were just high energy electrons. So alpha particles were not electrons, they were something else. They had a positive charge, and it was twice the size of the charge on an electron. And they were heavy. And by heavy, what I mean is that they had the same mass as a helium atom. So compared to an electron, these guys were like monstrous, right? These guys were really, really, really big. So it's worth mentioning a little bit about some of these early investigators of radioactivity. Many of them died young because people didn't realize the health impacts of handling radioactive materials. So that was kind of something that happened. Marie Curie famously was sick throughout her life. She ultimately died of leukemia. She'd often have like burns on her hands and so forth, and a lot of illness from handling these materials. Her documents become contaminated. Her apartment became contaminated. She used to apparently sleep with radioactive materials because she liked the glow of them and things like that, and had no understanding of the health consequences. Okay, so Ernest Rutherford, he was an interesting guy, and he knew that alpha particles were positively charged, as I mentioned, that they had twice the charge of an electron, and that they were really, really heavy, 4 times the mass of a hydrogen atom, which makes them the same mass as a helium atom. And he also knew that alpha particles, when they were emitted by a radioactive element, were moving very, very fast, hundreds of miles per second. So he knew that these guys were heavy and moving quickly. So Ernest Rutherford had this grand idea. What about if you took a beam of alpha particles and smashed it into a sample of matter and watched what happened? Maybe you could break off another type of subatomic particle, or maybe the way that the alpha particles scattered would tell you something about how atoms were put together. So he devised this thing called the Geiger-Marsden experiment, which is named after the two students who carried it out. And so what he asked his students to do was to take a gold foil, and the reason that he chose a gold foil was because you can hammer gold until it's just a few atoms thick, and then expose it to a beam of alpha particles that are emitted from a radioactive element. And what he was expecting was that if the plum pudding model was true, these alpha particles, because they were so heavy and because they were moving so fast, they would travel through the atom completely undeflected. And if that was the case, it would be strong evidence that the plum pudding model was on the right track. It was said that the alpha particles should go through the foil like bullets through tissue paper. So let's have a look at what he did. So he gets a source of alpha particles by putting a radioactive sample of matter in a box that just has a pinhole in it, right? So it's a lead box, and lead can block alpha particles, and because it's got a pinhole in it, you're just going to get, these are positively charged, a beam of alpha particles. Then he erects a screen that's coated in material that glows when a charged particle hits it. He used zinc sulfide. So he puts this in a circle around where the beam is coming through. And then in the center of that circle, he puts his gold foil that's only a couple of atoms thick. So what he was expecting is 100% of the alpha particles would go straight through, right? If that was the case, then the plum pudding model was a reasonable explanation for the structure of the atom. What he found was this: most of the alpha particles do go straight through. A few are scattered at sort of modest angles. Some, not many, but a decent number are scattered actually behind the gold foil. So what does this mean? It means that most of the alpha particles go through like there's nothing there. So most of the gold foil is not very dense at all. However, occasionally the alpha particle hits something that is so dense that it stops the alpha particle dead in its track and bounces it backwards. And so when you do the math on this, you realize that whatever these alpha particles are hitting has to be insanely dense. So it's kind of like if you were firing a machine gun at a piece of tissue paper, you would expect 100% of them would go through, right? It would just go straight through like there was nothing there. But this is like if you were firing a machine gun at a piece of tissue paper and occasionally, a bullet came back and actually hit you. Right? Most of them do what you expect, but every now and then one comes back and hits you. So, at the time, Rutherford kind of explained this using artillery shells. He said it was something like if you fired a 40-inch artillery shell at a piece of paper and it bounced back, that's how unlikely it was. So the only way that Rutherford could satisfactorily explain all these results was like this. He said, as most of the alpha particles pass through the foil, most of the foil must be empty space. That makes sense. And then he said, as some alpha particles are deflected or bounce back, then there has to be something that is positively charged to repel the alpha particles that contains nearly all of the mass of the atom. And he called this the nucleus. And the reason was because you had to take the plum pudding model of the atom with its diffuse matter and its tiny little electrons. He knew it wasn't the electrons that were doing the deflecting, and you have to squish all of the positive part of the atom down to a tiny little pinprick, and then you're going to kind of leave the electrons out there, in order to get the density of matter that would be able to deflect or bounce back one of these alpha particles. So you've got to squish that positive stuff down into what he called a nucleus. Okay, and then the math worked out, you could explain the way that these alpha particles were being scattered. So Rutherford was very clever. He used a lot of the statistics of how these particles were scattered to predict the size of the atom and then the size of the nucleus. So he said the atom all the way across is about 10 to the 10 meters. And that is borne out to be true by modern experiments. But then he said the nucleus, the positive part of the atom, which previously was the spread across the whole atom in the plum pudding model, is only 10 to the minus 15 meters across. So that's all the positive stuff, right? This is all the positive stuff. That's the pudding shrunk down to a point. So what fills in the rest of this space out here? What makes up the negative part of the atom? And it can't weigh much, right? So what takes up the rest of that space? It has to have almost no mass, and it has to be negatively charged. Well, it's kind of obvious now, isn't it? When you think about it, it's got to be electrons, right? So this led to the Rutherford, or what's sometimes called the planetary model of the atom. So what you have now is that the positive charge of the nucleus is a result of positively charged particles that he calls protons. And then he says that the electrons move around this nucleus that contains protons at a great distance from the nucleus, just like planets move around a star. Okay, so you've got electrons out on the edge of the atom, and then you've got protons all bundled together in the center of the atom. Now, of course, this presents a lot of problems. Is why do the protons stick to one another? Wouldn't they repel one another because they have the same electrical charge? So this is going to kick off a whole nother round of discoveries in nuclear physics. So even still, Rutherford can't get the density of the nucleus to be enough in order to deflect the alpha particles in the way that he was seeing. He still couldn't get enough mass into the nucleus. And it took about 30 years to get to the whole thing resolved. And it was actually a guy called James Chadwick, who was Rutherford's graduate student, who actually resolved this issue. And he discovered a particle called the neutron, which has zero electrical charge, that also sits in the nucleus alongside the proton. Now your nucleus is heavy enough to explain all the results that we're seeing. So what do we end up with? We end up with the familiar model of the atom. It looks kind of like the logo for the TV show Big Bang Theory, right? Where you've got this nucleus. It's positively charged due to the presence of protons, but it also contains neutrons. And then a long way from that nucleus are the electrons. Now, most of these diagrams, or almost all of these diagrams, are never drawn to scale because the electrons are so far away from the nucleus. Remember that the total volume of the atom is a sphere that has a radius of about 10 to the minus 10 meters, and of that, the nucleus is only 1/100,000th of that volume. Right? So the nucleus is tiny in comparison to the total volume of the atom. So the atomic theory that we're going to be using, the updated theory from what Dalton proposed, considers that the atom is comprised of a dense nucleus that contains nearly all the mass of the atom, and that nucleus is made of neutrons and protons, tightly bundled together. Because of the presence of protons, it's going to be positively charged. At a great distance from the nucleus are negatively charged electrons that are very light. So we know the masses and the charges of all of these subatomic particles now. So the electron has a charge of -1, and the proton has a charge equal and opposite to that of the electron of +1. The neutron is electrically neutral and has no electrical charge. in atomic mass units, the mass of the electron is pretty much negligible. So when atoms gain or lose electrons and form ions, their mass doesn't change. Keep that in mind for later on. Protons and neutrons have a mass of about 1 AMU, and neutrons are a tiny little bit heavier. Most people will use E superscript minus to indicate an electron, and they will use P superscript plus to indicate a proton, and then normally a lowercase n to indicate a neutron. Occasionally you'll see people use just a P, a lowercase p for a proton, and some people will use just the lowercase e for an electron, but that's pretty uncommon. So atoms have no overall electrical charge, and what that means is that they contain the same number of protons as they do electrons. So if you know the number of protons, you automatically know the number of electrons, and vice versa. The number of protons that is present in the nucleus of an atom is given a special name. It's called the atomic number, and we give the atomic number the symbol Z. The number of protons is just equal to the number of electrons, so Z is also equal to the number of electrons in a neutral atom. Now, what's important for us to recognize is that every atom of a given type has the same number of protons. It has the same atomic number. So all hydrogen atoms have atomic number 1, all helium atoms have atomic number 2, and all lithium atoms have atomic number 3, and so forth. And if you look at the periodic table, you'll see that the numbers are organized in order of increasing atomic number. So the atomic number is generally written in the periodic table above the element's symbol. There we go, and that's the atomic number. So Z is always a whole number, because you can't have, part of a proton, right? So if you're ever wondering what one it is on the periodic table, it's always the whole number. Okay, neutrons, they don't have an electrical charge. And it turns out that for a given atom type, the number of neutrons might vary. So you could have a helium atom. There we go. Now all helium atoms have 2 protons. Most helium atoms also have 2 neutrons. But you could have a helium atom that has 3 neutrons and 2 protons. It would still be a helium atom, because the type of atom is determined by how many protons it has. So it's also important, because this number can vary, to define the sum of the number of neutrons and protons that a particular atom has. And this sum is given a special name. It's called the mass number. And just so you don't confuse it with the atomic number, they brilliantly decided to give it the symbol A. So something to keep in mind, because A includes neutrons and protons, A is always going to be bigger than Z. There's one case where it's not, and that's for hydrogen, because hydrogen doesn't have any neutrons. But the big number is always the mass number, and the smaller number is always the atomic number. Okay, so atoms that have the same number of protons, that is, atoms of the same type, but they have different numbers of neutrons, they're called isotopes. Okay, and so what we can do is recognize something that's really, really helpful. The number of neutrons that are in a particular isotope or particular kind of atom is just equal to the mass number, the big number, minus the small number. And why does that work? Well, the mass number is the number of protons plus the number of neutrons, and then the atomic number is just the number of protons. So you can see there that the number of protons cancels out, and it leaves you with the number of neutrons. So the number of neutrons is just the big number minus the small number. So that's really easy to do. Okay, so you can have multiple types of atoms of a given kind. So you could have a carbon atom that has 6 protons and 6 neutrons. You can also have a carbon atom that has 6 protons and 7 neutrons. So it could get confusing, right? So how you can distinguish different isotopes is using what we call isotope notation. or sometimes it's called complete chemical symbol notation. That's a real mouthful. And what you do is you write the mass number, the big number, above the atomic number, the smaller number, and then you follow that up with the element's symbol. Now, it is important to realize that the mass number is not found on the periodic table. The other number that's shown on the periodic table normally has 2 or 3 digits after the decimal point. That is not the mass number. That is what is referred to as the atomic weight, and we'll learn how to calculate that later on. You can tell it's not the mass number because it's not a whole number. The mass number has to be a whole number, as you only can have a whole number of neutrons and protons. So here below are a few examples of this notation. So here we've got the carbon atom that has 6 protons in the nucleus, but a total of 12 particles overall in the nucleus. So this guy would have 12 minus 6, so it would have 6 neutrons and 6 protons. Here we've got a carbon atom. It's got a total of 14 particles in the nucleus, and 6 of them are protons. So this guy has 14 minus 6, so that's going to be 8 neutrons and 6 protons in its nucleus. And then we have a whole series of isotopes of hydrogen. Okay, now there's 2 things that are worth noticing. Every kind of carbon atom will always have atomic number 6. So it's kind of redundant writing both the atomic number and the symbol. So people will often, quite commonly, will skip writing the atomic number when they're trying to indicate different isotopes, because they know because it's carbon, it has to have atomic number 6. The other thing is sometimes people will want to write these out in words because they don't know how to do a subscript or a superscript on their computer. And so something like, let's not do that one. Well, let's do this one. Helium 2,5. We would call that helium, which implies that the atomic number is 2. Then we put a hyphen, and then we follow that up with the mass number. Okay? So again, you don't have to say the atomic number because it's implied by the name. So either of these 2 things are equivalent. You kind of get used to using both of them. Sometimes people will drop the atomic number just for convenience. All right, there is a little something that's worth mentioning concerning isotopes of hydrogen, and that is that they have some common names. So the isotope of hydrogen that has mass number 2 is called deuterium, and the isotope of hydrogen that has mass number 3 is called tritium. And you might see that as you kind of reading around. You probably heard of heavy water. Heavy water is water made where every hydrogen atom is deuterium. And so it's heavier than regular water because the hydrogen atoms are literally twice as heavy. So you've answered questions like this in Chemistry 139, but let's just do a run through now. It says, how many protons, electrons, and neutrons are present in a strontium-86 atom? So the first thing you want to do is you want to find the atomic number of strontium, because that's going to give you your number of protons and your number of electrons. And strontium is down the bottom in group 2A, and it has atomic number 38. So Z equals 38. And then you also want the symbol. And the symbol for strontium is Sr. So we can go ahead and now solve this pretty easily. From the periodic table, the atomic number of strontium is 38. So the number of protons equals the number of electrons. So the number of electrons is also 38. In the question, you were told that the mass number was 86. And we know that the number of neutrons is simply the mass number, the bigger number, minus the smaller number. So 86 minus 38 gives me 48. And the only warning I'm going to say here is use a calculator, because it's really easy to do mental arithmetic wrong when you're a little bit stressed. Okay, so that ends the section on the evolution of atomic theory. This kind of continues, particularly with respect to the structure of the nucleus, and we're finding that protons and neutrons themselves are made of particles, and we're discovering the forces that hold the nucleus together, and all those interesting things have been, ongoing and are still being worked out. But I hope you found this video helpful. Good luck with everything.